So in this video, I want to show you how to find the continued fraction expansion of any number, not just rational numbers. So for instance, before we found the continued fraction of the square root of 2 by using some simple arithmetic manipulations, but now I'm going to show you a more general method that you can use to find continued fractions of things like root 3, root 5, or even things like pi or e. So that's quite interesting. And the first step goes like this. We're basically going to define two different sequences. So we're going to have two sequences xn and an, two sequences of numbers, and we're going to try and find those numbers using an algorithm. And at the end, our sequence of an's is going to form the basis of our continued fraction. So the first step says that if we want to find the continued fraction of x, then we set x0, the first term in the sequence of xn's, to be our number x. And I'm going to say that a0, the first term in the sequence of an's, is going to be the floor of x0. Now, if you don't know what the floor function means, the floor is basically the largest integer which is smaller than x0. So for instance, the floor of pi would be the floor of 3.14159 and so on, and that would just be 3 because the largest integer, which is smaller than pi, is 3. And for instance, if you had to find the floor of 2.2 or 2.6, then the floor of 2.6 would be 2 because the largest integer, which is less than 2.6, is just 2. So it's a bit like the integer part of a decimal. Okay, so once we found x0, once we've written down x0 and a0, then we move on to the next step. The next step says we set x1 equal to 1 divided by x0 minus a0. So using these x0 and a0 terms we found in step 1, we can now define x1. And we're going to set a1 to be the floor of x1. So once we found x1, we just take the floor of that number to find a1. And then for the next step, x2 is going to be 1 divided by x1 minus a1. And a2 is going to be the floor of x2. And we're going to continue doing this until we basically spot a pattern. So the fourth step, well, it says that here, but then we define x3 to be 1 divided by x2 minus a2, and then we define a3, we take the floor of x3, and we continue doing that. Now, I do say that we continue until a pattern is spotted. You don't necessarily have to find a pattern. So, for instance, you could do this with the number pi, and to my knowledge, it's not currently known if there is a pattern for the coefficients in the continued fraction expansion of pi. There might be, but I think it's an open problem. But once you found these a0s, these an terms, then x is just going to be the continued fraction of a0, a1, a2, etc. So the terms in the continued fraction expansion are just going to be exactly the terms that we found in the sequence above. So it's going to be a0 plus 1 divided by a1 plus 1 divided by a2, and so on and so forth. So with that in mind, let's use that algorithm to find the continued fraction expansion of the square root of 2. Okay, so let's do that. So the first step says that we're just going to let x0 be equal to the number we're trying to find a continued fraction expansion of, so that's just root 2. And a0 is going to be the floor of root 2. Well, root 2 is something like 1.4 followed by some decimal places, so that's the floor of 1.4 blah blah blah. And that's just going to be 1, because the largest integer, which is less than 1.4, is 1. Okay, how about x1? Now I need to move on to the next term. x1, by definition of my recurrence relation, that's 1 over x0 minus a0. And that's just equal to 1 over, well, x0 is root 2, and a0 is 1 as above. So that's 1 over root 2 minus 1. Now I want to rationalize the denominator. That'll make it easier to find the floor of x1 to find a1. So I'm going to multiply the top and the bottom by the conjugate of the denominator, which is root 2 plus 1. I just changed the minus sign to a positive sign to rationalize the denominator. And what does that give me? Well, in the numerator, I'm just going to get this. So I'm going to have root 2 plus 1. And in the denominator, I'm going to have root 2 minus 1 times root 2 plus 1. And that gives me root 2 plus 1. All divided by what? Well, this is a difference of two squares. It's of the form a minus b times a plus b, so that's just going to be a squared minus b squared. So in other words, it's going to be root 2 squared minus 1 squared, and that's going to give me root 2 plus 1 divided by, well, root 2 squared is just 2, and 1 squared is 1, so that's 2 minus 1, and that's just going to leave me with root 2 plus 1. And that's my value of x1. Okay, so that's going to help me find a1. Now I know that a1 is just the floor of x1, and that's the floor of this number with root 2 plus 1. And root 2 is about 1.4, so root 2 plus 1 is about 2.4. So I need to find the floor of 2.4 followed by some decimal places which aren't important. And the floor of 2.4 blah 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 is just 2, because 2 is the largest integer which is less than 2.4 blah blah blah. Okay, so that gives me a1. Now I can find x2. x2 is just going to be 1 divided by x1 minus a1. And that's going to be what? Well, x1 was what? What value did I find for x1? Well, x1 is this thing, root 2 plus 1. So let's plug that in. So x1 is root 2 plus 1. And a1, which I just found above, has the value 2. So let's use that value. So minus 2. And that's going to give me 1 divided by root 2 minus 1. But hang on a second. If I compare this value, 1 over root 2 minus 1, I've already encountered that value in my previous calculations. So if I look at my calculation of x1, I already had this value over here. It was already equal to 1 over root 2 minus 1 before I started rationalizing the denominator. So what I've just shown is that x2 is this thing, which is also equal to x1. So this is also equal to x1. So that therefore means, that's x1, that therefore means that when I calculate a2, that's just going to be the floor of x2, but x2 is equal to x1, so that's just the floor of x1. But by definition, the floor of x1 is a1. So a2, so therefore a2 is just equal to a1. So what happens if we then do the same thing with x3? Well, if I did the same thing with x3, I'm just going to get x2 again. And that's the same as x1. And so when I calculate the floor of a3, that's just going to be the floor of x3, and that's going to be x2, which is equal to x1, and so on and so forth. So what does that tell me? That tells me that a3 is going to be equal to a2, which is going to be equal to a1. And that's because every time I continue doing this algorithmic process, I'm going to find that with x3, I'm also going to get 1 divided by x2 minus a2, which is again going to give me 1 divided by x1 minus a1, because x2 equals x1, a2 equals a1. So I'm always going to end up with 1 divided by root 2 minus 1. So there's no point in me continuing this sequence. I'm just going to get the same numbers. So let's recap what we found. We started with a0 being the floor of root 2, and we found that that had value 1. So let's put a circle or an underline over, under that. And then we found that a1 had the value 2. And then we found that a2 was also equal to a1, which had the value 2. And then we found a3, which had the value 2, because that was just equal to a2. And so all of the following numbers, a4 and a5 and a6, all of these numbers are going to be equal to 2, as we've just shown. So that tells us, so therefore, root 2 has the continued fraction expansion, a0 followed by a1, and a2, and a3, and so on and so forth. And using our values of a0 up to an, that's just going to be 1, because that was a0, followed by 2, and 2, and 2, and an infinite sequence of 2's. And if I wanted to write that in shorthand notation, that would just be 1 followed by 2 bar, which indicates that the sequence of 2's goes on recurring forever. And once I have done that, that's actually the same as 1 plus 1 divided by 2 plus 1 over 2 plus 1 over 2, and so on and so forth. And these numbers here, appearing in the continued fraction expansion of root 2, are exactly the a0s, a1s, a2s, a3s we just found. So in other words, this value, that was a0, and this was a1, and this was a2, and this was a3. Okay, so that's a very nice way of finding the continued fraction expansion of root 2. The reason why we made this algorithm is because it is possible to find the continued fraction of things like root 2 without going through this process, because root 2 is quite a simple example. But it's very important to use this for examples like the cube root of 2, or perhaps the square root of a prime, where the prime happens to be a very large number. And this is a process which always works, and you can use it to find the continued fraction expansion of things like pi, and we're going to do that in a later video. So in the next video, we're going to look at some more examples of using this algorithm for some harder examples. And if you like this video, please leave a like, comment, and subscribe for more content just like this. Thank you.